You almost done? Anybody need time? A little bit time? Okay, you are done. Good. Well, let's get it started. Happy Friday, and welcome back to computer organization class. So today, let's see what we already talked, what you learn about this module 6. Module 6 is about procedure, calling procedure. Is what at the end of this session, or maybe next class, next Monday, we're going to finish assembly instruction set in RISC-V. So, but in this class, we're going to continue again procedure. Last class, we explained the step that you need to do for procedure call. So you use procedure or function or method in high-level languages, and in this class, we want to let you tell you how use this procedure in low-level languages like assembly language. So what we learned, we talk about actually basic block. We said the basic block is a block that is important for compiler. It has just one branch in and one branch out. Between this, you don't have any reference. So that's good for a compiler to do optimization because it can actually combine instruction, can reorder instruction, play with instructions, and make them more actually pipeline friendly. The basic is that you want to make it kind of to can run on the pipeline properly. Pipeline is an issue. It's going to have lots of issues. We're going to see them later. We call them hazard. If two instructions not are set together, they're going to destroy the pipeline. So we need to, actually compiler need to play with these instructions in basic block to make pipeline to work better. So that's called optimization, kind of optimization, optimizing instruction sets. That compiler use basic block. We talk about that. We also talk about procedure. What is procedure? What is calling procedure? Of course, you had in other high-level languages. Procedure is a block of code that has a special purpose. It's doing a special task, and you might use it, reuse it many times. And this function or this procedure need to get called. We have one function that is a main function. We call that caller. And when we call one function, that function called callee. So this caller and callee making this procedure call. So in RISC-V also we have conventional form to deal with these procedures like normal. Always you need to pass parameters or arguments and transfer control and manage storage and return results. So this is like a conventional form for procedure that we need to do that in RISC-V. We talk about this stuff. The last part that we talked was actually, I'm just going to talk briefly today as well, the steps that we need to do for procedure call. These steps this is a complete form, but sometimes you don't need to do some steps. Like when you want to call a procedure, first you need to place actually parameters that you want to send to the procedure. So we have a specific registers for them. We call them argument registers. think one of your um, quiz question was about that, x10 to x17. These registers called argument registers, you use them for sending argument to the procedure, or returning back from procedure. You can use them. Mostly x10 and x11 for using for return, and rest is for actually sending argument. But it can be used for all of them. And when you put the parameters in these registers, you need to call procedure. Today, we're going to see more instructions for calling procedures. Mostly jump and link can be used. So jump and link also need to save returning address in x1. x1 is a specific register for just return address. You put that. When you use jump and link, like automatically it saves the next instruction, that is program counter +4 in x1. Okay, that's the next step. And then we, if we want, if we need, we can save x1 in another part of memory that we call it the stack. Why we save x1? Because this procedure might be not leave. It might be, it might call another procedure. So nested calling or nested function. So in that case, x1 gonna rewrite by others. So we need to save it somewhere safe. We can use a stack for that. Okay, so if you want to save that, we're gonna save that. How we save in a stack, we're gonna see today, but I'm just gonna pass fast this step and go deeply in each of them. What else we need to do? Sometimes we need to get more storage from a stack. If you are dealing with more parameters, or you are working with the memory inside a procedure, you can allocate more memory inside a stack, and then start perform the operation that you want to do in procedure. In procedure, it's supposed to do something, like for example, adding something and return back the result. You're going to do this adding in this step. After finishing, you put the result in one of return registers that I mentioned is x10, for example, if it's one. Again, here, sometimes return address, return values is lots of information. Maybe you can't fit them in registers. In this case, also, you can use a stack for that. And then you send the address of that block of information out. That's also possible. In high-level languages, also you have that. Call by reference. You can it call by value or call by reference. Okay, anyway, and after that, what else we need to do? We need to restore x1. So restoring x1, x1 is the address for return. So you need to restore that. Restoring that is like popping from a stack. So you're pushing to a stack and popping from a stack. In other courses, I don't know if you had data structure, probably you work with the stack and push and pop. But that stack wasn't a real, actually, a space. It was like abstract data type or data structure. Is abstract, it's not real. But this is stuff that we are talking is a real stack. It's a real memory that in consider as a stack in your computer. Okay, that's a restore x1 and then return back. Return back also has a specific instruction called jump and a load return. Jump and load return can be used for return. We're going to see them in next slide. So we talked about this last class, and we had example, but we didn't talk deeply. Now we need to go more deeper. First, we start with these two specific instructions for procedure calling. They call jump and link. So we have jump and link and jump and link return. Jump and link for jumping to actually calling a procedure, and jump and link return for return back from procedure. So how they work, jump and link, the structure is like that. Jump and link x1, because x1 is a return register. You put return address there. What is return address? Program counter plus 4. Automatically, this instruction can compute program counter. The program counter is the address of this instruction in instruction memory, and then add it by 4 and put the result in x1. x1 is one of those registers that is used just for return address. You're not allowed to change it or work with that as a normal actually registers. Okay, so so what's happening here? We are adding program counter. Actually, program counter is also a register that you are not allowed to like manipulate it or work with that. Some registers in RISC-V, they are accessible, like X1. But program counter is not something, you don't have any instruction to work with program counter. That's something that I wanted to tell you. Okay, program counter plus 4, gonna go to X1. This is how a jump and link works. And then jump to that label. This label is the address in instruction memory, okay? So in memory, we have different parts. One of the parts is called text part or instruction parts. Instruction is there. And this instruction part is just readable. You can write there. You just need to read it. You just can't read it. So it's just readable. We're gonna see the structure of memory soon as well. Okay, so that's for jumping to procedure. So how it works, address of following instruction put in X1, that is program counter plus 4. Why 4? Why 4, not 8?
Instructions are 32 bits.
Yeah, perfect. All instructions are 32 bits. In this actually machine or RISC-V structure. Okay, so we add that by 4 and put in X1 and jump to the target address. That's for jump. Another instruction is for return. After finishing, you need to return, you know. So normally, this is the main function. So you jump and then do, this is caller, this is callee. You run this and then return. So when you do return, you can use jump and link register. That's another instruction. The format is like that. So we are doing kind of dynamic jump because this is a register. So that can be used for other applications as well, you know. What normally doing this instruction gonna use this X1 address because X1 address is a return address, and add this index to that. Because it's 0, we're just going to jump directly to x1 and actually start start executing the main function or caller function. The rest of the function without any problem. So normally, we need to write that in a way that not any problem happens. So when I'm talking about not problem happen means if you are changing here something, if you are changing some, for example, registers, you need to return them back as normal. Whatever was before, you need to bring it back. If you change that, when you come to the color, that's already changed. So the data gonna destroy. So you need to save that and return that back. You can use a stack for that. Yes. This one, this is okay. Very good question. Jump and link, it still has and link. It's still this store. This is like a destination register for the next instruction. So after this, I don't know application, but probably there is some application for that. I can check that. What is the application? Anyway, it's going to put the program counter +4 in x0. But x0 is always 0. You can't change it. But you can use another register to make another application. One of the application of using any idea, what other work we can do in addition to return from procedure to the main with this instruction. Look at this part. This part has something interesting. It's a dynamic jump. Dynamic jump. So any application coming to your mind, like application that you are using in high-level languages, you can use this. Do you think you can use this instruction for that? Do you have any dynamic jump in for example, C++ or Java or Python?
Switch case.
Switch case. Yeah, switch case is one of them. Yes, you can make switch case with that, because switch case is you are jumping based off some conditions in different actually addresses or different parts. So you can play with that. So yes, that's something interesting that you can use for that. So this is making dynamic jump. So x0, oh, actually here I mentioned that. X0 is register destination. The next instruction address gonna be there. Here is x0, but you can put any other registers to save that. And what else? Yeah, and as you mentioned, we can use other applications like switching case with this, because it's dynamic jump. Okay, another part that we already touched up last class was leaf and not non-leaf procedures. Normally, when we are dealing with procedures, some procedures just you run them and they finish. They don't need another helper. They don't need another function to call. So those procedures or those functions called leaf. So normally they don't call any other procedures. They are not nested. Nested means you don't have another jump and link inside them. Okay, so when you call them, it's like this. This is the main. You call them, and it's return. No more problem. So this is caller and callee. This is leaf. Why it's called leaf? Because it's a tree structure. So so that's, for example, the caller call another helper. We call it callee, for example. If this callee call another callee, for example, callee 1, callee 2, callee 3, callie 4. So in here, we just have these two are leaf procedure. The rest are non-leaf procedures. Why? Because this procedure, for example, has another jump and link, because jump and link to this callie, and that one also the same. Callie 1 also called not just callie 2, callie 3 as well. So they make a tree structure for calling procedures. Okay, so that's different between leaf and non-leaf procedures. For leaf procedures is simpler because sometimes you don't need to use a stack to manage information, especially if it's very small. For example, if you want just compute a value, and that value can be fit in these arguments registers, even you don't need to get extra memory. You can use those registers and return back, and you even don't need to worry about x1 because they're not gonna overwrite it. Okay, anytime you call jump and link, x1 gonna get overwritten, overwritten. So that's why you need to consider if it's leaf or if it's not leaf. Okay, that's for leaf. Leaf is simple. Let's go for non-leaf. Clean this up. For non-leaf procedures, the caller, when the caller call another callie, that callie might call another callie. So we have nested function or nested procedure or nested jump. So we use another, and this is when this happening, x1 gonna get overwritten. When it get overwritten, we need to save it somewhere. Where? Memory. What type of memory? A stack. We're gonna see that later. We need to save a state. Oh, we need to save a state in memory that's called a stack. We're gonna see that in the next slide. And also, if you have return, you not just return address, you also sometimes need to save other information as well. For example, you have some temporary registers that callie work with them. So maybe this temporary register already used in main procedure as well. You need to use them and return them back. So that's why you save them when you want to go inside. You store them in a stack, and when you want to come back, when you want to return, you restore them back. So this is happening in calling procedure. We're going to see example. Example of that can be like a function that has some helper, or nested functions or recursive functions are like that. You will see one of them in your assignment. The new assignment is a Fibonacci function. I think you need to implement it. Okay, so that's when we're dealing with actually non-leaf procedures, and we need to return correctly. Okay, so let's see what is memory layout in this part. So we already talked about memory layout. Memory layout in RISC-V has these steps, these parts. First part is the reserve part that we not work with that, or instructions are in a text part. Sometimes this called like the instruction memory. So the program counter point to that. Program counter is a pointer that actually specify the instruction that need to get fetched from this part. This part is readable, is only readable. Is not writable. You can write in this text area in a memory. Another only readable part is static data. Static data is also some variables are a static variable in high-level language. You see them, for example, in C++, I think you have a static variable. Those variables going to be here. Some global actually variables you can use this part of memory for global variables. Global variables are variables that can access uh, with many procedures, so that they are global. They can access by everybody. Okay, and then okay, this global pointer point to that. You have a specific register, actually X3, that called global pointer, and you can access to that using actually load and store. So when you use load and store, you have offset that is 12 bits. Okay, and then the rest is the dynamic data that called heap also. So when you are starting from lower memory to higher memory, this is the address increasing, but a stack is actually combining with this dynamic memory, but a stack pointing. We have a stack pointer that point to the stack, but a stack is kind of grows downward. So that's an interesting part about that. When you want to put something in a stack, first you need to decrease the stack pointer and then put that inside. So this is the characteristic of a stack, is grows downward. Oh, so that's the interesting part. If you want to put something in a heap, is upward. When you put that, you add the address. But when you put something in a stack, first you decrease a stack pointer. How many? 8 most of the time, because we want to put a register, and registers are 8 bytes, 64 bits. So we mostly work with 8. Even if in some examples, one of the question in your assignment, you have a C code that use integer, but still you use double integer for them. If I use integer, you consider here 64-bit for each register, because we don't want to make it complex. You can use lower, but it's going to be so complex. So you just use 64, even for integer one. The rest going to be 0, of course. Okay. So that's something that we need to know. That's the memory layout. So we talk about this a little bit. So let's go for a stack. We also talk about the stack too much, but we didn't like explain it more deeply. So a stack is part of the memory that used for temporary storage during programming. So the properties is actually is like a data structure. In higher languages, you implement that as an abstract data structure, but here is not abstract, it's real. So the structures is last in, first out, or first out, last in, LIFO, last in, first out. The one that come first, go last, or last in, first out. Same. So it's like that. You put the last gonna be here. So and when we want to pop something, you need to take from the last. So the first is actually going to be the last that can be popped. So we put something inside the stack with push and take something from a stack with pop. So we have these two instructions. How we implement them, we're going to see them. So they grows downward. That's the interesting part in a stack, in the memory. Why we do that? Any idea why we have this structure? So this was a heap. It's going this way, and a stack going this way. Why we did this? The rest are, for example, why you think we have this structure? Why a stack is downward and heap is upward? Yes.
So no other memory gets in the middle of the stack.
Yeah, it's more usable. You're not waste anything. For example, if you use here stack upward, so this part may be not used. So, but in this case, you can use all of this. It's going to be more efficient. So the efficiency is very important. That's why we had that like that. Okay, that's important. Thank you. It's a good question. Lower addresses as data is pushed. So how we manage a stack? We use a stack pointer, of course. A stack pointer is pointing to a stack. Let I clean some part of this. Okay. So a stack pointer pointing to a stack. Anytime you want to put something, you use this stack pointer. A stack pointer is one of the registers, actually, x2, considered as a stack pointer, and always points to the top of the stack. And oh, that's a picture. Better, clear way. And why a stack is needed. So so a stack kind of preserve register values when you go to procedures. So you can preserve registers because registers are limited. We don't have unlimited registers. They're going to finish. Some big program's going to use all of registers. So what we do the rest, if we have procedure calls, we need to save them and restore them. Where? In a memory. Which part? A stack is the best area to do that. Not just that, but also this return address or x1. We can save two values in the stack. We can save return address and callee actually can and save registers. Save registers like registers that caller was using before. For example, some temporary registers. And this callee wants to use them again. It's better to save them, use them, restore them back. Maybe caller was using them and had some values inside them. So that's why we don't want to destroy it. Okay, so we can see some examples soon. Store local variables. So if you have local variables, still you can use stack for that. Support nested and recursive functions, as I explained before. So this is one example how we pop and push. So first stack pointer is here. When you want to push these three registers, first you decrease this 8 values to point here and then put that. Put x5, for example, and then put x6, and then put x20. And after finishing, we start popping. When we pop them, we increase this every time when we pop by 8. Decrease here, increase there. That's a push and pop. So here is push, and here is pops. Okay, that was example for that. How a stack can be used. Um, they are all repeated. Here is the important part. How you do push and pop. To do push, you need two instructions. First, you need to add a stack pointer, actually kind of decreases a stack pointer or decrement a stack pointer. When you do -8, it's like decrement a stack pointer 8 elements, and then do store data. So these two instructions add a stack pointer 8 and store double word, whatever register that you want to store, you can put in stack point. That's a push. And for pop, how you pop, first you need to load from memory that stack pointer point there. Index is 0 because it's directly there. And then we return back a stack pointer. We added 8 unit. So add immediate stack pointer and 8. So this is push and pop. That is important part. So let's see one example here. So here we have a function that has 4 arguments and doing some mathematical operations. We use those registers for them. So normally what we need to do, first we need to save these. So this is a leaf procedure. We don't call another inside them. So the label is leaf example. The first step is to x5. So we have 2 temporary variables, x5 and x6. Why they are temporary? Because we are thinking the main function using them, and we want to save them. So it's already mentioned that these 2 are temporary. So we need to save them somewhere. Okay, so we save them. First, we decrease a stack pointer, and then put save with store data. Put actually x5, x6, and x20. What was x20? X20 was actually another one that, oh yeah, x20 is the callee saved. So because x20 is another one that the caller might use it, we need to save that because we are using that here. Whatever register that you are using in caller, you need to save them because you are changing the value of them, okay? Let's back to that. So this is how we do that. First of all, we decrease that 24. However, you can do -8 and put this, and then do another -8 and do this, and do another minus. But with this, you can make the instruction less. First, you decrease 24, and then put a stack pointer like that. That's easier way. So after saving those, you do operations. The operation was just computing g plus h and j plus 1, and then decrease them together and put f. F is x20. So as you can see, we played with these registers. We need to, that's why we save them. Right now, we return them back. So copy F to return register. X10 is a return register. And restore X5, X6, and X20 as we did. As we save them, right now we restore them from a stack because they are in the stack right now. We restore them, and then bring them a stack pointer back, because we decrease minus 24, we increase it now, and return to the caller. So that's a small, simple example of leaf procedure. Next class, we're going to see non-leaf procedures. It's a little more, complex than this. Any questions? Okay, have a great weekend.